Hey everyone, and welcome to The Explainer. Today we are unpacking an absolutely incredible, ambitious scientific initiative known as the DO-CIRC project. We're going to look at what is, honestly, a totally paradigm-shifting approach designed to solve two massive global environmental problems at the exact same time. Think about it. We've got this colossal mountain of construction waste we generate every single day, right? And on top of that, the excess carbon dioxide we're constantly pumping into our atmosphere. Well, what if I told you that we could actually use one of these problems to solve the other? It sounds wild, I know, but it's a fascinating concept with massive, real-world implications. And today, we're going to show you exactly how it works.
Okay, let's dive into this. Here is our roadmap for the explainer today. 1. The construction waste crisis. 2. The DO-CIRC solution. 3. Monitoring recycled materials. 4. The CO2 mineralization process. 5. Testing re-recyclability, and we'll wrap it all up with 6. Building a circular future.
So, Section 1, the construction waste crisis. Let's set the stage.
The construction industry's footprint is just incredibly heavy. Look at this staggering statistic. Construction and demolition waste accounts for a massive 37.5% of all solid waste in Europe alone. Globally, we are talking about over 10 billion tons of this waste generated every single year. 10 billion tons! When old buildings come down, all that rubble has to go somewhere. And right now, improper management of all this debris is leading to severe landfill shortages, widespread soil pollution, and just a huge loss of valuable resources. It is for sure an unsustainable one-way street of extraction and disposal.
Moving on to Section 2, the DO-CIRC solution.
The entire project hinges on this absolutely brilliant core scientific concept, CO2 mineralization. Now, usually recycled concrete aggregates have a big problem. They are highly porous, meaning they absorb way too much water, and that just makes for weak new concrete. Nobody wants a weak building, right? But in this process, gaseous carbon dioxide is actually diffused directly into the recycled materials. The CO2 dissolves in the pore solution and reacts with the old hydrated cement to form solid calcium carbonate and silica gel. Think about what is happening here. A harmful greenhouse gas is basically turned into a solid, strengthening agent that literally fills in the microscopic holes of the recycled aggregates. It locks the carbon away forever while boosting the material's performance. Talk about hitting two birds with one stone.
To prove this works not just in theory, but out there in the real world, the DO-CIRC research framework is structured around three core activities. First, they monitor real-world recycled materials. Second, they conduct rigorous CO2 mineralization and concrete mixing tests in the lab. And third, they assess whether this newly enhanced concrete can be recycled yet again when a building reaches the end of its life. Let's look at each of these phases in a bit more detail.
Section 3, Monitoring Recycled Materials. Let's talk about the reality of waste.
So the really crucial point is this. A lot of previous studies in this field relied on recycled aggregates that were, well, perfectly produced in a pristine laboratory setting. But you and I know that doesn't reflect reality. Real construction and demolition waste is messy. It's highly variable, it's full of impurities. This project moves completely beyond the lab by analyzing actual waste sourced directly from real-world recycling plants. They monitor these materials long-term to establish real baseline data, making absolutely sure that the CO2 mineralization solution actually holds up in the totally unpredictable field of commercial recycling.
To really understand why this treatment is so necessary, check out this comparison. We have untreated recycled aggregates and fines. Like we said, they are highly porous, they absorb way too much water, and they result in weak, degraded concrete performance. In the real world, you normally have to dump in a bunch of extra cement to make up for it, which completely defeats the environmental purpose, right? But after the CO2 treatment, these materials are transformed. The carbonation products increase the solid volume, making the material dense, dropping the porosity, and locking away the CO2. It allows these waste materials to perform almost exactly like brand new, freshly mined aggregates. It's a real game changer.
All right, Section 4, the CO2 mineralization process. Let's get into the lab.
Now, what's really interesting about this is the sheer scale and rigor of the testing flow. First, construction and demolition waste is separated into larger aggregates and smaller fines. Then, they're placed in carbonation chambers, where optimal conditions, we're talking CO2 concentration, temperature, humidity, are tested and tracked using highly advanced microstructural techniques like X-ray diffraction. After that comes the battery of physical tests. These newly carbonated materials are mixed into concrete and mortar, and then relentlessly tested for slump, compressive strength, drying shrinkage, and carbonation depth. They are basically proving, with hard, undeniable data, exactly how much better the carbonated mixture performs.
Now, I want to draw your attention back to a brilliant little detail in that process. Notice the inclusion of recycled fines, or RF. When old concrete is crushed down, about 40% of the aggregate produced is fine material, and a huge chunk of that is essentially microscopic dust, particles smaller than 0.15 millimeters. Historically, this dust is totally underused and just thrown away, meaning current recycling isn't truly zero waste at all. But DO-CIRC actively includes these tiny fines in the carbonation process, ensuring that absolutely no part of the crushed building goes to waste. The whole shebang gets used.
Moving to Section 5, Testing Recyclability.
Okay, so this timeline represents the holy grail of the project. It's one thing to recycle concrete once, right? The benefits of carbonation for once recycled aggregates are definitely becoming more well-known. But what happens when that new building, the one made of carbon-infused concrete, reaches the end of its life decades from now? This is where DO-CIRC completely breaks new ground. They are physically crushing the carbonated concrete they created in the lab to produce second-generation recycled materials. They want to prove that you can re-recycle twice recycled aggregates. If successful, actually scratch that, when successful, this proves that concrete doesn't just have a second life, but potentially infinite lives.
Finally, Section 6, Building a Circular Future. Let's look at the big picture. When you combine all these phases, the real-world impacts are just staggering. By transforming weak waste into strong building materials, we drastically reduce our dependency on landfills and prevent illegal dumping. We simultaneously sequester carbon directly into the very fabric of our cities. And crucially, the materials needed for this, rubble and CO2, are readily available literally anywhere in the world. This means the project provides a highly transferable framework that any country can adopt to meet global climate goals, directly supporting massive initiatives like the EU Green Deal.
Which leaves us with this final, really provocative question. Is a zero-waste, carbon-negative future for construction finally within reach? By turning a harmful greenhouse gas into the very glue that resurrects our destroyed buildings, the DO-CIRC project strongly suggests that the answer is yes. It completely flips the script on how we view industrial waste, turning our absolute biggest liabilities into our most valuable resources. Thank you so much for joining me to explore this incredible material science. Until next time, keep questioning, keep learning, and keep looking for those brilliant solutions hidden right in front of us.